We're at the South Dakota School of Mines and Technology. This is the Thermodynamics homework solutions. This is for homework number 9, problem number 2. So this is other vapor liquid equilibrium. This is specifically on Henry's law. How do I know it's Henry's law? So the problem that we're doing is out of Koretsky. It's 8.46. It says, what is the solubility of oxygen and methanol at room temperature in 1 bar? What is the solubility of oxygen and methanol at the same temperature but 100 bar? Oh wow, okay. And so I have to consider, well, I have to consider kind of two things here, but it's all about solubility. Solubility just screams Henry's law. Okay. So let's first approach this problem from the standard conditions. Now, we're just going to use Henry's law, for kids, so to speak. Okay, now, it says, so Henry's law says y1 p is equal to x1 Henry's law 1 and 2. Okay? Now, first off, we're going to assume that the pressure is high enough that the methanol is only going to be in the liquid phase. Okay, so we're going to assume that the Y1 is pure oxygen. Okay, so this goes to 1. Okay, and so the X1 is really simple. It's just the pressure divided by the Henry's law constant. At those standard conditions. So the pressure is 1 bar. The Henry's law constant I can look up in the table in the book. It's easy enough. It's very straightforward. There's really nothing more to it than that. Okay. Now, where it gets tricky is, okay, now I have to think about 100 bar. And so I can no longer use Henry's law for kids. I now have to use Henry's law for PhDs. Okay, so Henry's law for PhDs says Y1 V1 hat P equals x1 gamma 1 over gamma 1 infinity. Henry's law constant naught times the exponential, well, just Henry's law constant, and we're gonna have to adjust it. Okay. The other thing that now we can assume it's probably an ideal solution. That it's infinitely dilute and so on and so forth. So it pretty much is an ideal solution. Okay. So our Y1 in this case, and we're still going to assume that it's pure. Okay. And if it's pure, we're going to assume that the fugacity coefficient is that Lewis fugacity rule applies. And so X1 simplifies down to V1P over my Henry's law constant. Okay. Again, Lewis-Randall. Now, where am I going to get phi? Well, it doesn't say anything about an equation of state. It is pure, and it doesn't say anything about it being steam, and so that means I'm going to use my Lee-Kessler tables to get my fugacity coefficient. Now, I'm not going to go through the math of that. We've done that enough that you can do that on your own. But that is where I'm going to get phi, and I am going to have to get phi in this case. Now, obviously, I'm given P and Henry's law constant. Okay, now Henry's law constant, we do have to adjust because the pressure is different. Okay, so if you remember that the natural log of Henry's law constant, dP constant T is equal to partial molar V1 infinity over RT. Okay, and so if we separate and integrate, Henry's law constant, 1, 2, is equal to, Henry's law constant over the original Henry's law constant is equal to the exponential of from P naught, which is going to be 1 bar, to P, which is going to be 100 bar in this case, partial molar V1 infinity over RT dP. Okay, now we're assuming that our V1 infinity is constant. Is that a good assumption? Yeah, I mean, 100 bar is still high, but we can still assume that it's incompressible. And that is even more applicable when we're talking about V1 infinity. Okay. And so, well, now I just integrate this, okay, so that, you know, my new H12 is going to equal my original H12 times exponential of partial molar V1 infinity over RT times P minus P naught, which is going to be 99 in this case. Okay. So the real tricky parts here is A, I have to adjust for pressure, and B, I cannot forget about Lewis-Fiaschi rule. Okay. Sorry. I can't forget about Fiaschi coefficient. I'm going to use Lewis-Fiaschi rule so I don't have to at least do a mixture. Okay. And that will give me my new solubility. But there's nothing more than that. It's truly just solving for x.